is the impact of the matrix data structure on the performances of the sparse matrix vector kernel. Basically, this presentation is a collection of the results we achieved in the task 3.1 of the exaFOAM project. The partners involved in this task are three: CINECA, which is the leader one, and BSC, Barcelona Supercomputing Center, and NTUA. So let's start with, so I will start with an introduction on the data structure that we have in the vanilla OpenFOAM code. So just some reminders of, probably some of you already knows what I'm going to say, but it's a recap of some concepts that are useful for the next one. So basically, OpenFOAM is as you know, is a toolkit for discretizing advection diffusion equations using the finite volume method. Okay, so the discretization of this kind of operators generates a matrix. Okay, so a discrete representation of the operator, which has a symmetric sparsity pattern with a full diagonal. Okay, so the developer of OpenFOAM in the 90s designed the code in order to exploit this data structure. Okay, so the idea is to decompose the matrix A into the sum of three matrices. One which is diagonal, represented by D, a lower triangular matrix represented by L, and an upper triangular matrix represented by U. Since D is a diagonal matrix, it can be represented and stored in memory as a dense vector. Okay, because while for L and U, since they are triangular matrices, we need to store also the sparsity pattern. Okay, but since the sparsity pattern is symmetric, okay, we can store, we need to store only the sparsity pattern of L or U, one of the two, in order to reduce the amount of memory to be stored and transferred during the running of the kernel. If the matrix is not only symmetric in the sparsity pattern, but also is totally symmetric, also the values need to be stored only for the one of the two, lower or upper. So the idea of the work we are going to present is that the matrix is decomposed into these three diagonals, three matrices, L, D, and U. Okay. Basically, I can define a family of LDU storage formats by defining the way I'm going to store the sparsity pattern of L or U. Okay, because yeah, this is basically a decomposition of a matrix. Okay, LDU doesn't mean anything related to the LDU decomposition that you can find in a linear algebra book. It's basically is splitting, okay, into three matrices. But I need to define how the sparsity pattern is to be stored in memory for L or for U. Okay, and in OpenFOAM is used a COO, which stands for coordinate format variant. Okay, basically I'm going to use a COO ordered for L, a COO ordered for U, and dense representation for D. Since we are going to use COO for the triangular matrices, we need two vectors basically to represent columns and basically ij positions of the values in the matrix. And these two vectors in OpenFOAM are named owner and neighbors, because these two vectors have a strong relationship with owner and neighborship of face respect to adjacent cell in the mesh. Since we want to, let's say, use the same sparsity pattern for U and L, okay, basically the U values are stored per rows and the L values are stored per columns. Using this very nice strategy, we can use, we need to store basically the CO format only for the triangular upper matrices. This is an example of a 2D representation of a Laplace operator, okay, over a stencil using finite difference. Yeah, it's a very simple example, but here I'm going to show that in order to represent this matrix using the LDU ordered CO variant of OpenFOAM, we need basically 5 arrays. Basically, the diagonal vector, which stores the diagonal values, upper, which stores the values of the upper triangular matrix, and lower, which store the other ones. Upper address and lower address, which are also named owner and neighbors, basically, as you see, store the row position and column positions of the value of the upper triangular matrix. As you see here, upper address is ordered, no? Is a consecutive, so the ITH plus 1 position is higher than the previous one. Why? And lower address is not compressed. No? As you see, you have repetition of values for all the values of that belongs to the same row. So if you have, let's say, 8 values for each row, you have the same row position in multiplied by 8 in memory. Okay, so a lower address is not compressed. The question is, can we define other way of storing the sparsity pattern of L and U, maintaining the splitting of the matrices into LDU? The answer is yes. Okay, so we can, for example, use CSR, the compressed sparse row format for U, and CSC, for example, for L. This is a very it can be implemented easily in OpenFOAM because it doesn't require any cell reordering. If I, for example, want to use CSR for L and U, I need, it's possible, but I need to reorder the mesh. I can use, for example, LPAC or Celsius sigma for L and U. We can basically define whatever I want in the representation of L and U. I don't know if this gives you some benefit or not. I'm going to show some results at the end of the presentation. MSR and full MSR and full CSR are not LDU variants. Okay, so they do not belong to the family, to this family, because in MSR basically L and Y are together CSR compressed. The diagonal has been separated. In CSR, L and D and U are all CSR compressed. So in this slide, you see basically the C++ representation, okay, of the Sparse Matrix Vector kernel using the LDU ordered CO storage of the matrix. So basically it's pretty similar to the code you have in OpenFOAM. And on the right, you see, for example, the LDU CSC CSR variant belongs to the same LDU family. Okay. What are the main difference between the two codes? So the similarity is that since we have this LDU splitting, basically we have the same loop, multiply the diagonal part to the x or solution vector. So the first loop is the same on both on right and left. The loop is different for the off-diagonal part, because for the LDU order Giovanni, we have basically a single loop, and a loop is over the off-diagonal values, which is equal to the number of faces of the mesh. And we have this, let's say, sort of X loop or cross loop, I don't know, because you see you have owner and neighbor in the first line and neighbor and owner on the second line. So you see that owner and neighbor basically design a sort of X. But we have a single loop exploiting the fact we have basically two vectors for representations, so to store the positions of the values of the matrix. If I want to, let's say, approaching the CSR, the full CSR variant by reusing this LDU splitting of the matrix, we have two for loops, one nested into the other. The first is over the number of cells, n, and the second one is we have a loop over the number of non-zero per row, which is represented here by n call. The problem is that in general, for whatever mesh you get from a mesher, n call is not a constant parameter. N call depends on the row. Okay, so so here for a, let's say, generic mesh of OpenFOAM, this loop cannot be unrolled easily by the compiler. If n call is, for example, constant, basically is equal to 3, the second loop can be unrolled, and also the branch prediction can do a perfect job. But this is not the case for a generic mesh. So we define a parameter that we call the jump parameter or jump coefficient, which is defined as the ratio between the number of jumps with respect to the number of lines of rows of a matrix. What is a jump? How a jump is defined? A jump is defined as a situation in which the ith line has a number of non-zeros different from the previous or the sequent row. Okay, basically is and this jump coefficient basically measure how many jumps, okay, there are in the matrix, so how many variations in the number of non-zero in the matrix respect to the normalized respect to the number of rows. Okay, what we and so we compute this jump coefficient for two very famous benchmark in OpenFOAM: the 3D lead-driven cavity and the 3D motorbike. Okay, this is a mistake. There is no cavity, motorbike. So, what you see is you see that the jump coefficient is very different from the two cases. Lead-driven is very, very low, 0.02. In the motorbike, you have this very high number, 0.711. Okay. Then we try to run, let's say, the two cases, okay, by using 6 different sparsity patterns. The variant implementing OpenFOAM, which is called here for sake of brevity LDUCO, the RCM permutation of LDUCO, the LDU sorted by the number of values per row, and then we have LDU CSE CSR, the same with RCM permutation, and the variant by sorting with respect to the number of non-zero per row. Okay, what are the main results of this very simple test? If we look at LDU, okay, you see that the performances, okay, moving from LDU-CO to LDU-RCM-CO, basically you see the speed up is basically is equal to 1. So there is no basically advantage in the receiving cavity from moving to LDU-CO to LDU-RCM-CO. For the motorbike, you get a benefit, okay, the speed up of 1.36. If we, let's say, sort the matrix by the number of non-zero, you see that the time for the motorbike cavity grows a lot. For the lead-driven cavity, there is no basically, yeah, it's a little bit slower, but there is no big differences with respect to the standard case LDU-CO. If we move to LDU-CSR, you see that basically you have that moving from LDU-CSR to LDU-RCM-CSR, in the living cavity, the performances are slower. For the motorbike, performances are better. If we use the sorting by number of non-zero, lead-driven cavity is the faster, okay? While for the motorbike, as before, the performances grows a lot. So our conclusion is that that since the lead-driven cavity has a very low jump coefficient, okay, so it means that the matrix is already sorted by the number of non-zero. Introducing this totally raw permutation basically doesn't modify too much the performances. For the motorbike, if we introduce this jump coefficient, if you introduce this sorting by number of non-zero, you see that the performances are very, very bad. Okay, while the RCM give you a very strong benefit, and RCM is an algorithm that reduces a lot the bandwidth of the matrix. So RCM is useful, very useful for the motorbike. Sorting by rows, not useful. For the lead-driven cavity, RCM is, let's say, doesn't give you a very useful advantage, while sorting for the give you some benefit, in particular when using LDU-CSR. This is the sparsity pattern, a visual representation of the sparsity pattern for the motorbike with 1 million of cells. On the left, you have basically the sparsity pattern representation when you run SnapX mesh as in the tutorial by refining, by using a more refined subblock grid. And on the bottom, you see basically the number of non-zero of the matrix. You see you have sort of this a lot of variations because you have the jump parameter is very high. If we apply RCM, you see that the bandwidth of the matrix is very reduced. Okay, but the sparsity pattern has still have a very high jump coefficient because you see a lot of variations in the number of non-zero. If we apply the raw permutation by sorting the lines with respect to the number of non-zero, you see that the bandwidth of the matrix is basically full. You have a bandwidth equal to the number of the number of rows, and the sparsity pattern now is a sort of steps. Okay, you see. So here we have, for example, 100,000 lines with 2 values, 3 values, 4 values. Okay, they are sorted. So design and define, let's say, an algorithm that try to combine the two algorithms and the two advantage of the two previous permutation. We want to combine RCM that reduce the bandwidth of the matrix, and it reduce and minimize the cache miss penalties, and combined with the raw perm that try to reduce the jump coefficient and try to minimize the branch misprediction penalties. This can be the two algorithm can be combined in chunks, and this algorithm has been named by us as RCM block row pair. And we found, and is described in a deliverable of the project, that you can get an optimal number of blocks that, let's say, found that minimize the jump coefficient and the bandwidth by taking the advantage of the two algorithms. Here is a graphical representation of what I said. Now, for example, in the picture on top left, you have 3 blocks, no? And you see that the bandwidth of the matrix is still high, so beta is normalized, but it's still high, while the jump coefficient is very, very low. If we use 50 blocks, okay, the matrix approaching the full RCM permutation, you see that the bandwidth represented by the beta parameter now is very small, 0.059, while the jump coefficient is still a very low value. So jump coefficient generally increases very, very low by increasing number of blocks, while beta decreases very, very fast. So this is regarding the permutation that we introduced in OpenFOAM. Okay, so now we can exploit this data structure in some blocking by modifying also the way I perform the loops. Okay, since we have now blocks, okay, where the number of rows are at the same number of columns, okay, we can use the previous code that I showed before, put in ncol as a constant, okay? He's represented in this loop by n. In the previous slide here was represented by ncol. So now here n is a constant parameter, okay? This function is templated, and n is the template parameter, okay? Basically now the loop is not anymore, as you see before, basically the loop is a loop over the subblocks, where each subblock has a constant number of non-zero, and you have a switch case that basically call the function with the n constant. Since these functions are templated, we see we have, say, the best performances for each value of n. So basically here the compiler tried to unroll the branch prediction here is perfect, and we also tried to, say, a little bit modify this code in order to let the compiler vectorize, but for meshes generated by Snappy or block mesh, there is no advantage in modifying this loop in order to allow the compiler to vectorize. But for sure, unrolling works, and also the branch prediction are reduced because n it's negligible, because n is a constant parameter here. In the next, but these are, let's say, improvements that have not been introduced in the deliverable, but have been tested after the end of the Discretization activity, was to, let's say, introduce our RCM block row permutation with the variable size of the blocks. Okay, try to have blocks that are, say, smaller in the corner and bigger in the center. Okay, we try also the variant of, since the blocks are very small, try to compress the column index by using an integer representation that has a less memory footprint. For example, we store only the offset respect to the diagonal, and if the blocks is small, we can use, for example, integer 16 representation or integer 12. Another variant we try is to apply the Celsius sigma inside to each subblock. Basically, for each subblock, we identify C rows. C could be equal to the AUX register or to the number of threads if you want to go to GPU. But let's see is a very small number, okay? And for the C rows, the values are reordered by column instead to be ordered by row, and by making this permutation inside this subblock of the subblock, we can introduce more easily and more efficiently vectorization for CPU and for GPU. In the next slides, I'm going to present some results. Okay, we achieved by generating matrices, or matrices with of different number of rows for 5K to 50K. Okay, and also we in the test I'm going to show we use two different sparsity patterns. One which is generated by block mesh, so it basically is a mesh which is composed by pure hexahedrals, and one generated by SnapPeak, which is an hexadominant mesh. So we have basically a huge number of hexahedral and few tetrahedral or polyhedral meshes, polyhedral elements. But the major part are hexahedral cells. We also made some tests with polyhedral mesh and tetrahedral mesh, but since they are not complete, I didn't report the results using these two kind of meshes in this presentation. Only block mesh and SnapX mesh, by varying the number of rows. We also run all the tests in parallel, which means that each core loads a matrix of size that move from 5K to 50K. So for a single node, the matrix is much bigger, because it's this size multiplied by the number of cores of the cluster. So in CINECA, we basically run the test using the tier 0 and tier 1 cluster we had the moment last year when we ran the test. So Galileo 100, which is an Intel-based cluster, and Marconi 100, which is a Power PC-based cluster. Okay. As you hear from this picture, the results depends on the cluster. It is obvious. The results depends on the cluster we are running the test. Okay. The nice result is that block row perm was the fastest solution in all the clusters with respect to the other formats. Basically, we found that if using very few number of blocks, specifically six blocks for matrices with 50K rows, basically is the fastest solution with respect to the other number of blocks. Okay. If we, let's say, talk about Marconi 100, we found that for both hexahedral and SnapX mesh meshes, the default, so the vanilla, let's say, or LDU order sequence or representation of the matrix with the RCM permutation is only slightly slower with respect to the permutation we define in this work. So the performances are not too much different, both for X and SHM. The difference is on Galileo, because we found that the MSR variant and the LDU CSE CSR variant are faster than the default storage in OpenFOAM, but block perm is faster than respect to MSR and LDU CSE CSR. Then BSC try to make other tests, okay, in order to see if they get the same results we got on our cluster by, say, using as for the test as storage the default implementing OpenFOAM, which is CO. Sorry, a full CO, the LDU CO that you have in OpenFOAM, LDU CSR, MSR or full MSR and full CSR. They basically run the test using 4 kind of meshes, 2 motorbike with different number of cells, a parabolic fan, which is sort of diffusion, heat diffusion problem, and a airfoil. So they made this test on Mare Nostrum 4, and they found that the full CO and the LDU CSR variant are the slowest. Okay, LDU, it can be, let's say, competitive, but never reach the performances of full CSR and a full MSR. These are the results they found with using BSC. Starting from these results, they, let's say, introduce in the sparse matrix vector kernel a parallelization, okay, using the OpenMP library, using 2 and say this OpenMP library is being used using 2 kind of shell memory algorithm. One is the classical fork join, and the other one is using the OMP SSS task version 2 developed in BSC. And they basically compare LDU CSR respect to CSR and MSR for the, as before, airfoil with 3 different kind of meshes, and motorbike with 3 different kind of motorbike. All these tests have been run on Mare Nostrum 4. If I remember correctly, all the results have been obtained by running the test on a full socket of Mare Nostrum 4. And what they found is that the maximum speed up possible is 1.2 respect to the slowest LDU CSR format. And MSR has been found faster in all the situations. In parallel, the other partner, NTUA, try to explore, okay, the performances of other, let's say, storage formats that can be implemented in commercial and non-commercial libraries, like, for example, MKL, provided by Intel, or the SparseX library provided by NTUA. So CSR variants like CSR variant 5, or one uses blocking, the LPAC. So they try to explore different and several storage formats that are found in literature to see if they can be faster or not with respect to LDU. And they basically basically run the test on two cluster, one which is called Epix server, which is based on AMD, and the other one is based on PowerPC. The test generates different conclusions. The results here are plotted on the, you see here, gigaflops, okay? On the left, you see gigaflops for all the matrices I mentioned before. So one based on XMesh or one based on SnapXMesh by varying the size. And they found that the gigaflop increases and basically reach a plateau around 45K rows in all the situations. So basically, and they take this this size, okay, and they run all of this kind of storage formats, and they found that on Epic server, MKL is the faster. LDU is not the slowest, but is not faster. Basically, is in the middle, okay, on Epic. If we move to on Power, you see that LDU, okay, is the faster is the faster data structure. Is a little bit faster if we use the EVM compiler respect to GCC, but looking at the other so Sparse 6 or the other variants of CSR, they are all slower respect to LDU. So this is in contradiction on what we get on the previous cluster. Okay. Also, the gigaflops, by say varying the number of rows, they do not increase and reach a plateau. They say decreases, moving from 5K to 50K rows. Okay, so my presentation is concluded. I can, let's say, sum up. I want to spend just 1 minute more to, let's say, draw a conclusion of this presentation, and by saying that using the meshes that you can get from Snappy or Block Mesh or other mesh like CFX, I don't know. Since the matrices in OpenFOAM are, let's say, generated for only for scalar, okay, only for scalar equations, okay, the number of non-zero per rows are not so high, okay. If also they split the matrix into LDU in order to exploit the symmetric sparsity pattern, the number of non-zero in L or U is basically half of what you get in using a full CSR or full MSR. So it's very complicated to exploit vectorization, and also it's complicated to be faster with respect to the default one. Basically, so in other words, the this LDU CO variant has been designed 30 years ago, but was considered as a very nice way of storing the matrix and performing the Sparse Matrix Vector kernel. So as you see here, you cannot get very huge performances by modifying the sparse data, modifying the data structure, and also the performances. So depends on the cluster you get. So you can implement an algorithm that is faster on Epic and slower on Power. Yeah, this is not obviously a nice result. Blockroper try to, let's say, reduce this variability. So we as you hear from the presentation, we do not cover all the possible results, but it looks promising. The idea is to complete all the tests and publish the results as soon as we have all of them, and we have a global view of what we get so far.
Thank you, Simone. Thank you very much for your interesting presentation. And do you have any questions? So we have time for one or two quick questions.